My name is Micheal Thomas. I work with the LIGO Livingston Observatory for the California Institute of Technology. In contrast to some of the earlier talks, I'm not going to be talking specifically about what LIGO does and all of the fascinating and interesting science that we do, but more about how LIGO is monitoring our Condor clusters. Just briefly, for anybody who's not familiar with LIGO, LIGO is a gravitational wave observatory, or more specifically, a pair of gravitational wave observatories, one located in Livingston, Louisiana, and one up in eastern Washington State on the Hanford Reservation. And LIGO's goal is to detect and catalog gravitational waves, primarily being generated through binary black hole mergers. LIGO first detected one back in 2015 and has since been doing a lot more detections of binary black hole mergers and other related events as sources of gravitational waves. A little bit of my background with Condor. I actually started as an HPC admin at Caltech, back on the Caltech campus in Pasadena for the CMS experiment, where Condor was being used to manage job submissions for the CMS Tier 2 cluster. In 2011, I transitioned to LIGO and took over HPC management of the computing cluster at the LIGO Observatory in Livingston, Louisiana. Even though I've been a LIGO user, or a Condor user, user in quotes, because it's more of a Condor admin than a user, I never really had the time to take a deep dive into Condor. Really, I was only able to spend enough time with it to just keep it running. And when I was managing the CMS cluster, that was a little easier because at the time, CMS had a much more limited use model. The jobs to the cluster only came in through a pair of OSG compute elements. There was no local job submission. So we just had to make sure that remote submissions into the cluster were working, and that was it. And a lot of the tier 2 clusters for CMS at the time were configured in a similar way, so we could all just kind of share notes on how things should be done. So I never really had to learn too many of the gory details about how to configure and run Condor. LIGO, however, has slightly more complex use cases. We do allow local job submissions, so we're now accepting jobs coming in from the OSG. And we are also submitting jobs locally to either the local cluster or to the OSG. So it's a little more in it to configure. However, I still never learned a lot of the nuts and bolts. Condor has a lot of knobs that you can tweak to configure it, and I just never really, if you've done any HPC administration, you're probably familiar with always getting distracted by something else that's broken that grabs your attention, and that seemed to happen to me quite a bit. So what are the problems that I was really trying to solve here? I wanted a web-based tool that would allow me to look at the health of my Condor pool, my Condor cluster, and do at least a limited drill down to help find out what's going on and where problems might be. I want to be able to see different views of the cluster status, both aggregate views and drilling down into schedu views or per user views or per tagged job tag views, and even information about how the GPUs are being used. I want to see how these evolve over time. I just don't want just a snapshot, because a lot of times if a problem happens, it might be transient and go away. So you never get a chance to see when it happened. One of the important things I wanted to be able to answer is when a user reports a problem, where are they submitting their jobs from? Because that's where you're going to go to try to get the information. And unfortunately, users are not very good about telling you where they're submitting their job. They say, hey, I have a problem. I say, okay, well, which host did you submit from so that I can run a Condor queue on it? And they said, oh, I'm running at Livingston. And so, well, we have 7 or 8 head nodes. Which one are you submitting from? And as it would turn out, they were actually submitting the jobs to different clusters. So I want to be able to just take a username and then find out where are their jobs being submitted from. And Condor's got a lot of CLIs to help manage the pool and to get status about the pool. But there's also a lot of class head attributes that you can key off of to try to get more information. And I've just never been able to get my head around all the different ones. They do change over time, new ones get added. One of the solutions that we had looked at was Condor Ganglia D. However, we have been having scaling issues with Ganglia on our cluster. And we ended up having to split things up into multiple subclusters in Ganglia, which required running multiple Gmon Ds. And it was getting to be a little cumbersome to get Condor Ganglia D integrated with that. Plus, it didn't always report the data that we wanted. So what was the solution? So finally, I spent a good weekend, a good long weekend, and did some Googling and came across an old HTCondor Week talk from 2016 about FIFEMON, which was developed out of Fermilab. FIFEMON is a Python service that uses the Python bindings into Condor to gather metrics from HTCondor and dump it into a time series database. And then Grafana is used as the front end for actually visualizing that data. So I've got links to the original presentation here and the Git repository that holds the original FIFEMON code is here. So you could say, hey, I'm done, problem solved, everything's good. Well, not quite. Things didn't work out of the box, which is not unexpected. We needed to do some additional work to these FIFEMON probes to get them to work in LIGO. One of the things is that the accounting tag information in the FIFEMON probes use some semantics that are specific to Fermilab. When Fermilab was using these to monitor on their HPC cluster, they embed the name of the experiment as part of the accounting tag. Well, not only does LIGO not use accounting tags, we also don't have any extra experiment to add on to this. So I had to change the use of accounting tags to LIGO search tags and use our own hierarchy for that. And then a few other minor changes that we had to make to the code to allow for dots in usernames, add GPU accounting so we could see how well our GPU resources were being used. And the Grafana dashboard that was provided was not quite functional with the changes that I had to make. So because we already had experience creating Grafana dashboards, I just ended up creating a new one from scratch. And then because I'm a packaging junkie, I put this all into an RPM to make it easier to deploy to on other clusters. And then I have a link here to all of the changes that we ended up having to make to the FIFEMON code. So the next few slides are screenshots of what we ended up with. So this is the Grafana front end that's showing us just an overview of what we've got on the cluster. We can see how many jobs are running, how many are held, how optimized things are being used in terms of CPU and memory, what the GPU utilization is, and then a nice time series plot of how these have all evolved over time. Next slide is a breakdown of the jobs per user. So when we want to see who the large users of the cluster are, we can quickly see here in terms of both running, idle, and held. The next slide just gives you a blown up view of the running jobs and the users plus how many jobs they're running. We can also take a look at the jobs on each schedu. We have about 6 to 8 different submit hosts on our cluster, and we want to be able to see where the jobs are coming from, which ones are being used the most, so that if we have an underutilized schedu and a user says, hey, I can't get my jobs to run because maybe that schedu is overloaded, we can now redirect them to one that has a few more, that doesn't have as much usage. And then here's just a blown up view of the running jobs per schedu. And then the The one that I've found to be one of the most useful is the plots of the number of users submitting to each schedule. So this is a list of all our schedules, as well as the number of jobs, which includes running, idle, and held jobs for each user on each schedule. So when a user says, hey, I'm having trouble getting my jobs to run, they're on hold or they're all sitting idle, I don't have to go back and forth with them a few times just to find out they're not even running on this cluster. I can quickly go and see, oh, hey, they actually are. They're submitting from this host. Now I can log into that host, run Condor queue, find out why their jobs are being held or maybe why they're not being matched. So the time it takes to actually start diagnosing a user's problem has been reduced quite a bit. And then we also do a limited amount of GPU monitoring. And we haven't found that Condor provides a lot of data about the GPU usage. Things like, the GPU memory that's being used isn't really there. But we can at least find out if users are using the GPUs or not. We have about 45 of our cluster nodes have GPUs in them, some of them multiple GPUs. And we just want to know if they're being used at all. And I'm glad I was able to actually capture this plot because in general, the GPUs at our cluster tend to be pretty idle. But I did manage to catch this where one user was using them at one point. We have additional plots that I won't go into right now, but we can look at the transfer queues on our schedules in terms of the number of uploads and downloads, active and waiting. We can look at the job efficiency for each user or for each tag, where the efficiency is basically defined as the total amount of CPU a job has used divided by the amount of wall clock time that's been used for this current job run. So if a job gets restarted multiple times, its efficiency will go down because their CPU time will go up, but their wall clock, CPU time, we can also look at aggregate CPU and memory utilization across the cluster. We can look at the amount of excess requested memory, or what I like to call wasted memory. And this is when a user requests to use, say, 8 gigabytes of memory, but they only end up using 2. That's 6 gigabytes that was reserved for them, but never actually got used. So we call that wasted memory. If this happens too much, we can contact the user and say, hey, you might want to tune down your memory usage. However, in a lot of cases, they just don't know a priori how much memory their job is going to need because it may vary across their collection of jobs. And then we can look at the aggregate dynamic slots that we have, CPU load, memory, disk usage across the entire cluster. So how has this been? This has been phenomenally useful for us. Even while developing the dashboard, we were immediately able to find issues with jobs on hold across multiple schedules. And then we're able to drill down to find out why some of these had been on hold for a couple of weeks, which was a little embarrassing that we just didn't know about it. Now we do. We found a couple of schedules that had a suspiciously round number of jobs running. It was, I think, actually 3,000 jobs exactly running. That was a little suspicious, and we quickly discovered that, oh, hey, we have to increase max job running on those. And that actually increased the utilization of the whole cluster because it turned out it was running on a schedule that was most heavily used. We found issues with memory requirements on jobs that were growing. We found that we have idle jobs, but the CPU and the memory across the cluster wasn't fully utilized. This is something we're still looking into. And this has also been extremely helpful to get an overview of the batch system health after we've done some maintenance. For example, last week, exactly a week ago, we upgraded to Condor 9.0, and we were able to find out that a bunch of jobs got put on hold after we did the upgrade. And after drilling down, we realized there was an issue with the UID domain setting on our cluster, which caused jobs to get run as the user nobody, but then they couldn't write their output to the user's home directory and they would get put on hold. So it was nice to be able to identify that very quickly and fix it the same day. What about the bad parts of it? Well, the time series database that we're using is called Graphite, and it tends to get overloaded pretty quickly. If you send too many metrics to it at a time, like on the order of 10,000, it'll start dropping some of them. So only a certain percentage of them will actually get written to the files. If you publish new metrics too quickly, for example, when you first start up or when a new user gets added, then it has a throttle that will limit the number of new metrics it will process at a time. So what we've learned is that when we start this up from scratch with a new Graphite database, we've got to disable this limit and let it create all of them, at least for the first pass. And then afterwards, let that throttle come back into place. The FIFEMON code claims to support the influx time series database, but we were never able to get that to work. It would be nice to try it out to see how it performs compared to Graphite. So what else is left to be done? Well, right now, this is running at the Livingston cluster and at the main LIGO cluster back at Caltech. We want to deploy it on the Hanford cluster, and hopefully we'll get that done in the next few weeks. We'd like to see more metrics regarding start Ds, to help us identify issues like, hey, we've got idle CPU and idle memory, but also idle jobs. That shouldn't happen. I think if we can drill down into some of the start D resources a little more, we could answer questions like that. Condor metrics D has come up a few times in some of my discussions, which is supposed to be kind of a successor to Condor Ganglia D. So it would be nice to see if we can help with the development of that and make use of that instead of running this specific FIFEMON probe. And I'd also like to see if we can get this data published into the Prometheus time series database. Prometheus has, if you couple it with the Thanos project, which does long-term storage into a Ceph cluster, it actually handles downsampled data quite a bit better than Graphite. With Graphite, as data gets older, it gets downsampled and you lose that original resolution. But with Prometheus and Thanos, data gets downsampled, but the original resolution data is still retained. So if you want to look at 1 minute resolution data from a year ago, you can do that. Obviously, it takes a lot more disk space, which is where the Ceph storage comes into play. Another obvious question is, well, now that we've got this working at Fermilab and LIGO's using it, what would it take to get this available for other people to make use of? And I think there's still LIGO specific features in this FIFEMON code. I'm not a Python expert, so I think if we were to make this more useful for other people, we'd need a Python expert to help us try to identify these experiment-specific features and abstract them out so that there might be some sort of a plug-in architecture so that other people can plug in their own monitoring, their own specific needs into it as well. We do accept OSG jobs on our cluster. However, at the Livingston cluster, that is not working at the moment and hasn't been working since we got this FIFEMON code running. So it's still a work in progress to see how the OSG jobs show up in our dashboard.
Sorry, Michael, you have 2 minutes left.
Okay, well, that's good because I'm actually done. I'm moving for questions, or I can also take the risk and do a quick live demo if you want to see some of the live data we've got on our cluster.
We are running behind schedule, so I think I would like to move on. I'm sorry, it's
okay, not a problem.
Very busy afternoon.
Hey, Mark, I at the end you mentioned something about the OSG jobs. are you running any of this on the LIGO, the worldwide LIGO, or whatever you call it?
I'm not sure what you mean by the worldwide LIGO. There's a
It's a separate Condor pool. I understand that these are the more local Condor pools that LIGO is running, or I got it wrong.
So LIGO has, so this is just for monitoring the HPC clusters that LIGO itself has paid for and manages. This does not monitor anything outside of LIGO's dedicated HPC clusters.